essentially the very elementary stuff that you might have forgotten. So it's just going to remind you of things you probably know. There will be a few things that you don't know about, but mostly it's stuff you do know about. This whole section is about probability, and start very simply with what is probability, some axioms of probability, and conditional probability, and then we'll move on to some standard distributions, standard discrete and continuous distributions that will show up later, particularly in queuing theory, and to some extent in game theory, but mostly in queuing theory. Poisson distribution, for example, shows up over and over again. And we'll end towards the next week with description of Bayesian networks, which is a way of talking about joint probability distributions over multiple variables. So it gets a bit more complicated, but it starts out pretty straightforward. All right, to begin with, so what is probability? There are many disputes about it, and in a few minutes I'll talk about different interpretations of probability. But from our perspective, what probability means is that we have some event that we're not really sure about. Okay, so for example, a classic example, you toss a die on a table, it has 6 sides, and you don't know which side is going to come facing up, so we cannot say this is going to happen, we don't know which number is going to show up. So since we don't have a definite answer, we can say, well, something is going to probably come up, and we can start attaching some numbers to it. So at some level, what we have with probability is that we have uncertainty. So probability is completely tied up with the mathematical representation of uncertainty. And so uncertainty is sort of a fact of life. We don't know what the stock market is going to do tomorrow. Apparently nobody else does either. So even the people on the stock market don't know what tomorrow is going to hold at this rate anyway. So uncertainty is a given, and one of the fundamental advances in mathematics which happened in the 16th century to 17th centuries was to recognize that it's possible to mathematically represent and capture uncertainty. So probability means uncertainty. How do you express uncertainty? In practical terms, what you're looking at is that you're building a system, okay? And in a system, what happens is normally you have some cause and then you have some effect. And typically what we'd like to do is when you have a cause, you have a definite effect. You do this, something happens. You press a button, something happens. And it's exactly what you wanted to happen. However, there are many cases where you don't know what's going to happen. You have some cause and it may or may not have an effect. For example, I can lecture to you for an hour. At the end of it, the effect is, I don't know, you may not remember anything a month from now, or you may remember something a month from now. So the cause is there, the effect, we don't know. So what we do is to represent this uncertainty in terms of probability. Now there are other ways of representing uncertainty, and they can have a big argument, and the AI people have been having an argument for many years, but what is the right way to represent uncertainty? We won't go into that, because all we're going to talk about is this particular approach, which is probability. Now, to make it more precise, what we say is this: we have that there is some cause, and the effect, instead of being this mushy cloud of, well, anything can happen, we be more scientific about it. What we say is that the effect is going to be an event, and that event can be enumerated in some fashion, either a finite or an infinite enumeration from a sample space. So what that means is that we are able to somehow enumerate or describe in some fashion the set of all possible events that can happen, or the effects that can happen, and then we'll say that the effect is one of these events that's chosen from the sample space. So again, we see the same kind of thing we saw last time with optimization. We're given a problem which is vague, and then we put on our scientific hat, and then we start building a model. And the way we build a model is we go and say, okay, what's the sample space? Okay. Once we start doing this, immediately things become more clearer. Instead of saying, well, I don't know what's going to happen, that's what a kindergartner would say. What you're going to say is, no, I don't know what's going to happen, but I know it's going to be one of these things, and then therefore I'm going to choose an event to be a member of the set called the sample space. Again, as I mentioned, the sample space can be infinite. All right. So let's take an example of this. I said one event, for example, was throwing a die. Now it doesn't mean that this is a fair die, it's just a die with 6 sides. So the sample space is just 1, 2, 6. So it's a set of 6 elements, and we call and the event actually is die shows 1, for example. That is the event, and of course we can just shorten it to P1. That's the probability of this particular event. Now, okay, so if it's it's a fair die, its probability over here is 1/6, but it may not be a fair die. We don't really care. I just want to show you the notion of a sample space and an event. Now, similarly, we can say tomorrow it's going to rain or not rain, or it could be sunny or cloudy. Whatever, we can say that the event space it's cloudy and sunny, for example, as the sample space, and then we can say what's the probability that tomorrow is cloudy. That's an event, probability of an event from the sample space. So we are basically focusing on this notion of events over here and sample spaces. Okay, any questions about this so far? So the important thing to notice is when you're mathematically representing any problem, you have to immediately start thinking, okay, is this the right sample space? Am I leaving something out? Are these the right events? Okay, because if you ignore some events, ignore some part of the sample space, then obviously your model is already bad. Okay, you already made a mistake because you can't even associate a probability with something, okay, if you can't put it in your sample space. You got to be careful about that. Okay, so once we have a certain definition of a sample space and event, we are actually in a position to start formalizing it. And the way we do it is through the axioms of probability. And now it turns out that there are many different ways of expressing the axioms of probability. And I'm going to show you sort of 2 ways, more or less. And they all have to do with representing these events, what do you think about these events. Now, what does axiomatization mean? Okay, axiomatization is a process by which what we say is we make certain statements, we make about probabilities, and we expect that everybody intuitively understands what it means. Okay, there can be no dispute about these statements because intuitively it's obvious to you this is true. Okay, now if you disagree with it, well then you're in a different axiomatic system. You say, okay, my axiom is different, well then that's fine. But as long as you're willing to accept these, then what the mathematical, the whole mathematical formalism says is, okay, you believe these, then through a series of theorems I can prove everything else from these axioms. In other words, the axioms are the bedrock upon which we build. And it can be shown that essentially everything in probability theory can be derived step by step from these 3 axioms. And where do these 3 axioms come from? It's intuition. Okay, so if you don't agree with them, then then it's not going to work. And the same thing comes, the initial process that started all this was in the Euclid, and where you had this axioms of geometry, which says only one line goes through 2 points, etc. 2 parallel lines don't intersect. These are the classical axioms, and then all of geometry can be derived from these axioms. In the same way, we want to derive everything about probability from these axioms, and it turns out it can be done. So these axioms are due to Kolmogorov, a famous Russian mathematician, and well, I'll just state them for you, and you can see they are pretty obvious. The first one is that if there is, so we are going to use the thing that event is represented by the letter E. So essentially, and the probability of an event is denoted P of E. So that's pretty standard notation. So what we're saying is the first axiom says 0 is less than or equal to P of E less than or equal to 1. Okay. So what does this mean? It says that the probability is a number, it's a real number that lies in the range 0 to 1. Now we have some interpretation of these numbers 0 and 1. Okay. Now as far as the axioms are concerned, it doesn't matter what 0 and 1 mean. There's no meaning. It's just a number in the range 0 to 1. After that, you can mechanically do whatever you want to derive everything from it, and just but we have some meaning intuitively, and this let me start with this. A probability of 1 intuitively means this event is definitely going to happen. So you can say with probability 1, the sun will rise tomorrow. Okay, so that is a probability 1 event because that is definitely going to happen. You know, in your at least limited time scale over the next, next 2.5 billion years, you can say it's a probability 1 event. After that, the sun may disappear. But anyway, in that time horizon, it's a probability 1 event. On the other hand, what does probability 0 event mean? It means that almost surely it won't happen. Okay, it doesn't mean it surely won't happen, but it almost surely won't happen. Then there's a very kind of a subtle difference over here. Probability 0 event it's a sort of this event that you basically should not happen. Okay, but here's an example where I can show you it will happen. So let's take an interval of a line in the range. I don't know, just 0, 1 for the sake of argument. And I'm going to pick a point at random from this real line. So I'm going to pick some point over here and just say, okay, that's my point that I chose. All right? Now, what is the probability of any particular point being chosen? Well, this line is of limited extension, it's of 1 unit, but it has an infinite number of points. Okay, it has an infinite number of points. So obviously any particular point being chosen has a probability of 0, right? However, if I add up all these 0 probabilities, I get a probability of 1 because I know for sure one of these points is going to get chosen. You see what I mean? So if I have an infinite set of things, I'm going to choose one from that set of infinite number of points. The probability of any particular point being chosen is 0. If I say, what's the probability that 0.5 is going to be chosen? It's 0, right? On the other hand, the sum of all these points is going to add up to 1. Yes?
I think you're talking about continuous.
Yeah.
Continuous, but what in the discrete?
In the discrete case, things are much easier. In the discrete case, probability of 0 means it's not going to happen. But in the continuous case, probability of 0 has a different interpretation, and it is an almost surely kind of event. And these kinds of paradoxes happen only in the continuous case. All right. So what we're saying over here is that we have this infinite, a sum over an infinite number of events. Because what is the event? The sample space here is infinite. It's the set of all points. The event is a particular event being chosen, and we're saying the probability of this event, we'll now sort of mathematically define it to be having a probability of 0, and we'll interpret that 0 as being sort of almost surely, with the understanding that the probability over the whole range actually adds up to 1. So 0 has a kind of a funny meaning, whereas 1 is clear. Okay, so this is where you start getting into these arguments about what is the meaning of probability 0. Okay, does it mean it never happens? Well, so the way I like to think of it is that it is going to almost surely not happen. There are different approaches to explaining it, and you can spend quite a bit of time on it, but I'm not going to. I'm just going to do that. Yes?
Don't you have the same problem with 1?
With 1?
Also be viewed as an event that will almost surely happen.
Well, with 1, we don't have this problem of summation over infinite sample spaces where each event is 0 and the sum adds up to 1. So yeah, you can come up with interpretations where 1 also gets a bit funny.
Like for example, in the example you just gave,
yeah.
You asked what is the probability of picking an irrational number?
Yes.
That would be 1.
Yes.
That is probability of that. You might just pick a rational number as well. So
oh yeah, right. So I'm saying if you can take this argument and kind of turn it around and say, okay, I'm going to do that. But I just, yeah, okay. So both 0 and 1 have issues, but I have more trouble with 0 than I have with 1. Okay. In fact, with probability 1, you choose a transcendental number. Okay. That's because there are more transcendentals than there are even irrationals. So you get into more trouble that way. But in fact, you might choose 0.5 also. So you get into measure theory, and I don't want to get into measure theory because that's really beyond the scope. So we have to start, if you want to really understand it, you have to study measure theory, and I'm not. Okay, so what you think of as elementary and simple concepts of 0 and 1 actually have quite a bit more depth to them. That's just what I wanted to highlight over here. Nevertheless, from the perspective of the axiomatics, we don't care how that number was chosen. We're just going to say it's in the range 0 to 1. We don't care what it means either. Okay, as far as we're concerned, here is a real number in the range 0 to 1, and that's all I care about. And the axiomatic approach has that power that says we're able to ignore certain aspects of the problem because we're doing that. Okay. Let me just continue with the second axiom, which is somewhat easier. The second axiom says basically probability of sample space, which equals 1. So in other words, you've got to pick something in the sample space. This is nothing more than saying that the sample space is a union of all possible events. So, well, something is going to happen. Okay, that's what that means. Or you can, equivalently, you can say P true, where true is Boolean true, is 1, and P false equals 0. This is another way of stating P true and false, or you might think of being definitions of true and false, whichever, again, what does true mean, what does false mean? Well, you can say, I can sort of mathematically state that from our perspective, true means it will happen, and therefore probability of true is 1 and probability of false is 0, but these turn out to be equivalent definitions. And so Kolmogorov second axiom is stated in one of these two different ways. And the third thing requires a little bit more definitional. So we need to define something. We define mutually exclusive events E1 and E2. Okay, so you're saying there are two events, E1 and E2, mutually exclusive. That means if E1 happens, E2 cannot happen. E2 happens, E1 cannot happen. So we cannot be in a situation where both E1 and E2 happen. Okay, so we're going to define that. And it's quite simple, to come up with E1 and E2. So basically we can define E2 to be not E1. Then obviously not E1 and E1 cannot happen at the same time. So it's quite easy to come up with these mutually exclusive events. And so what we say in the third axiom is that, so the definition of mutually exclusive is a probability of E1 and E2, which is also written as probability of E1 and E2, that's just some notation, equals 0. Okay. And I think in the notes I have said EI, EJ equals 0. What I really meant to say was probability, EJ equals 0. So if you define this in this fashion, then we can make the following statements. So given a set of mutually exclusive events, I'll just call them E1, EI, EJ, etc. These are just some index. Then the probability of the union of these events, I equals 1 to infinity okay. So I guess I don't even need J over here, EI plus 1. All right, so I'm giving you a set of events, a potentially infinite number of events, okay? I'm not saying these constitute the sample space, okay? I'm not saying that. I'm just saying I have a set of events and they're mutually exclusive, so if any one of them happens, then the other one cannot happen, all right? That's the definition of mutually exclusive. Now I'm saying, what is the probability of the union of these events? So in other words, either E1 happens, or E2 happens, or E3 happens, or E4 happens. If they're mutually exclusive, then I can represent that as a sum. So this allows us to introduce the notion of the summing of probabilities. And the summing of probabilities means that we are able to sum across elements that are mutually exclusive. Now, when I talked about the sample space earlier, I kind of said, well, these are the set of events that's going on. There is no reason for the sample space itself to have mutually exclusive events, okay? It doesn't have to be mutually exclusive. You can have sample space where you can have cloudy, sunny, partly cloudy, whatever, any combination you want. That doesn't mean that the events in the sample space are mutually exclusive. But if you consider those elements in the sample space that are mutually exclusive, then the probability that any one of those happens, this basically means any one, or you can represent it as this way using logical notation. So instead of union, I could have the or notation. Then the probability of the or of any of these events is the sum of the probabilities. Okay, and that's it. Okay, so another way of representing this, by the way, is also commonly used, just basically probability of E1 or E2. And now I'm not saying they're mutually exclusive, they're just any two events, is basically probability of E1 plus probability of E2 minus probability of E1 and E2. Okay, so you're saying if you have two events and they're not mutually exclusive, that's fine. We can add them up, and then you subtract away the common part. And the way to understand it is to use sort of this Venn diagram. You can say E1 corresponds to some space, E2 is this. So if I do E1 plus E2, I'm getting this E1 and E2 twice. So if I subtract it out, of course I'm going to get the overall union. So this one is obviously E1 and E2. So there's a fairly simple geometric explanation of why we need to do this. So E1 or E2 is a union, and to do this, and there's a set theoretic implementation, set theoretic interpretation, which is straightforward. We can think of E1 as constituting a certain sum of elementary events. That is these ones here. These are the elementary events over here, and then we take their union. We're going to remove those sort of sub-events or something that lie in this part over here. Okay, so then that kind of comes up as well. So there's a deep relationship between set theory and probability over here. Okay, so that is essentially the three axioms for Kolmogorov. Just to state them because they're raised. The first one basically says probability lies in the probability of an event lies in the range 0, 1. The second one says that the probability of the entire sample space is 1, or the probability of true is 1. The third one defines mutual exclusivity of events, and then we have a rule for how do we add mutually exclusive events. Sorry, how do we compute the probability of the union? It's just the sum. Okay, and these are the three things. Okay, let me stop and take a break here, and I guess I can put these two, and then we'll go on after that talk about the interpretations of actually came from China. Anyway, more on that later because I just finished reading that book. Okay, so what are the interpretations of probability? So when somebody says probability of event equals 0.25, what does it mean? And again, as I said, lots of work has been done, and I'm going to present sort of three approaches that people have used in order to give some semantics to it. And the first approach is what's called, counting arguments. And the counting arguments is essentially combinatorics. Okay, so I'm saying, okay, there are n ways of doing this, and this is equally likely ways. So if I divide it out, it's something. So for example, I have a die. I throw the die. So this is the classic thing: a die with 6 faces, and all of them are equally likely. That means the probability of any particular thing is 1/6, and that's it. It's a counting argument. And these counting arguments can be quite a bit more sophisticated. You're probably familiar with the balls and urns kind of thing, where you have some number of containers, often called urns for no particular reason, but I may have certain number of elements in here, and I may choose a certain number. I put them back, and depending on how you choose these balls from these urns and what colors they have, these can get fairly complicated, and I will not go into them other than to remark that as long as you assume that it's equally probable to choose a particular ball from a particular urn, then all of the other math works out. But it all boils down to counting arguments. And so with these counting arguments, we can come up with mathematically precise, discrete probabilities, okay, like 1 over 6 or 1.25, 1 over 4, right? You can just do that. And that's fine. But that doesn't do everything for you. The second approach, which is called the frequentist approach, basically says that all probabilities actually arise from the limit, as you know, limit sort of number of experiments tends to infinity, some metric on the experiment. Okay, so we have some experiment, we keep doing it, and we take the limit. So to take an example, to compare these two, let's say I have a coin and I flip it, right? It has a head or a tail, it's a fair coin. Now I say, what's the probability that it's going to be head or tail? Well, let's say, well, there are two possibilities, head or tail. We'll ignore that it lands on the edge. And so it's going to be 0.5, and that's a counting argument. There are two possibilities, each is equally likely, so it's 0.5. The frequentist approach would say, no, actually, how did you know there are only two possibilities? How do you know they're equally likely? You just kind of made it up, right? You actually didn't know that. What you've done, in some sense, is to do a series of experiments, and over a period of many experiments, you find that about half the time, you find that the metric, which is head or tails, is heads, and the other half of the time it's tail. So as you do an infinite number of experiments, or as you tend over here, this ratio will tend to 0.5. So what you really have is essentially the limiting value of some distribution. So if one were to actually plot sort of the number of flips over here, number of flips of the coin, and we're going to plot over here p head, what we can expect is that we have sort of 0.5 over here, and the number may actually oscillate, but eventually what we see is that the oscillations will die down, and we'll get this steady state where the limiting value is going to be 0.5. So that's called the frequentist approach, and their position as a philosophical approach is that there are no other probabilities other than frequentist probabilities, and everything can be viewed as in terms of an experiment. Okay, so we can take an example of this. By the way, this is the approach that's most often used in computer science, or in computer systems, networking systems. That's what is often used. So just to give you an example of this, what we'll do is, let's say I have a link, and then I have some source, and this source is sending packets on this link, and let's say they're TCP packets and UDP packets. And so there's, if I look at it, there's some packet over here, and the header says TCP or UDP or other. Okay, so I want to ask this question. I pick a random packet out. I just kind of look at some random packet. It's coming in the middle or at the end, and I say, what type of packet is it? It's a perfectly reasonable thing to do. Obviously, there's some uncertainty because it could be TCP or UDP or something, and so we can enumerate the sample space. It's TCP or UDP or something else. So three elements, and I want to know what's the probability. Okay, so in the counting argument, well, there's no counting argument here. Because there's no, I can't really count anything per se. There's no mathematical object going on. But there's a very simple frequentist approach. And what that says is, I'm going to take all the packets coming out. I'm going to put them in one of three bins. I'm going to put them in the TCP bin, and in the UDP bin, or in the other bin. And then I'm just going to put them over here. And then I'm going to, let's say, get 1 million packets. And let's say there are maybe 500,000 TCP packets and 450,000 UDP packets, and there's 50,000 other packets, and the sum is 1 million. Then I'll say, okay, probability of UDP, okay, is going to be basically 450,000 by 1 million, which is 0.45. Okay, that is a frequentist approach in the sense that we are saying million is large enough. Million is large enough, so things kind of get averaged out. That may not be true, right? For example, let's take the other end of the picture. I look at just 3 packets coming out. I get 3 packets, I put 1 here, and 2 end up here, and nothing is the other. Then I'm going to say probability UDP is 2/3, right? Because I got 3, I got 2. Well, you say, well, 3 is too small. 3 is too small. And then, well, how do you know 3 is too small? Well, it intuitively doesn't seem enough. What you really can do is this. You can say, well, I'm going to start plotting this graph over here. On the x-axis, I'll have the number of packets, and the y-axis, I'll have PUDP, and I'll see whether it settles down. Okay. Now, we don't know if there's some kind of higher level time scale. All right. For example, it could be the case that somebody is using BitTorrent over TCP, and so it kind of bumps up the number of TCPs, and then in 2 months from now, in fact, the number of UDP is going to go up because some other application comes and UDP goes up. So at this point, we're kind of in a big trouble because we don't know what infinity means, right? We're saying the limit as exponent tends to infinity is over here. So what's going to happen in the graph is that we have this oscillation all over the place, okay? And then it settles down. You say, oh, this is great. And you say, aha, I now have a steady state. Well, guess what? That wasn't a steady state. It suddenly is going to go like that. And maybe it reaches a steady state over here. Okay, because a certain traffic pattern changed. Or you could be measuring for an hour, everything looks fine, and then, morning breaks, people start firing up the web browsers, more TCP comes up, and suddenly the probability of UDP goes up or goes down or whatever, right? So, a fundamental issue in any kind of frequentist approach is that we cannot achieve infinity in real life. Okay? And so what we assume, or what you're forced to assume, essentially is that if you reach this period, it's called the stationary period, that the system is good enough, we measured enough. And one of the biggest problems when you do any kind of simulations or any kind of analysis or measurement study is, what does it mean for things to be stationary? And the general assumption we have here, and the general sort of working hypothesis, because we have to do something in real life, is we say, okay, this period looks long enough, we may draw a chart, show that it looks okay, and we hope, and we do this frequently, we do this enough times so that, things kind of settle down. But at the back of your mind, you need to be worried, because frequentist approach only, depends on this being infinity, and it depends on convergence of the probability value, and the probability value may never converge. There will be some dynamics such that the probability value never converges. So even this notion of 0.5 is suspect, because this looks like 0.5, but then at some point it may change, right? So you have to keep that in the back of your mind. But having said that, the frequentist approach, assuming convergence, can give you actual numbers that you can work with, and so this is what we use. Okay. Any questions about this? Yeah. So the question is, why can't, I'm repeating questions because somebody told me in the video, it was mine, I think, right? You can't hear the question. So the question is, why can't you use counting arguments over here? What counting argument can you use over here? I mean, the thing is that this is not like balls and urns. It's not a die. This is a link where stuff is coming out. I can look at the ratios, but that's a frequentist approach. Counting argument says, I have some mathematically decided prior that says, okay, if I have a die, it has 6 equal faces.
Yeah, but you don't have domain knowledge that you did have in the previous case, right? In the previous case, you assumed that the die was, or the coin was unbiased.
Yeah, so you're arguing on my side, okay? You're saying there is no domain knowledge. I'm saying, yeah, if you don't have domain knowledge, you're forced to use the frequentist approach. The counting argument approach works only when you have domain knowledge.
But if you had domain knowledge, even in this case, you could do something.
If you had domain knowledge, yeah, so if you're saying if you have domain knowledge, you could make the claim, yes. But in most practical networking situations, we do not have that kind of domain knowledge that allows us to say probability of TCP is 0.5 because that's the way it is. This is a traffic by its very nature is uncontrolled. We don't know what's going on. Okay. Any other questions over here? Okay. So the third approach, okay, so that was just an example of the frequentist approach. The third approach is what's called the subjective probability approach. Let me just erase this over here. Okay. So subjective approach. We have the same link, and I want to know the probability of UDP on that link. What do? I call up my friend who works for CAIDA, which is Center for Internet Dynamics at UC San Diego, and I say, hey, what's the probability of TCP? He says, I think it's 0.45. I said, great, I can put that in my paper. Okay, how does he know it's 0.45? He's an expert. That's his job. Okay, so the expert said so it's 0.45, and that's the end of that. Well, that sounds a bit flaky, but actually it's true. You go to a horse track and you place a bet on a horse, and you say,